In this example, we're looking at a mechanism which is made up of two links. The links here are OA and CB. OA is pinned to ground at O. BC is pinned to ground at C. And we have connecting these two is a slot which is cut in link BC, and end A of OA is constrained to be moving in that straight slot. We're looking here at a position where BC is a vertical. OC is always on the same horizontal line, given that we know the distance L between A and C at this instant, and we know that BC is rotating in the counterclockwise sense with 6 radians per second. What we want to do is find the angular velocity of link OA and the value of L dot. How does the distance between A and C change in time? Okay, so let's go through our process here. I'm going to start out with the easier part here. I'm going to look at OA first. OA are on the same rigid body, so VA we can say is equal to VO plus omega OA crossed with the vector which goes from O to A. O is a pin, so VO is a 0. OA we don't know. We're going to write that as an unknown. I'm going to implicitly assume here it's in the counterclockwise sense. Not important. One way or the other is fine. Just stick with it all the way through, and your math will tell you whether that assumption is correct. The vector which goes from O to A. O to A, we know that the link is 500 millimeters. The position here, L, is equal to 400, so we know that this distance here is 300. So from that we can find the angle of theta. So theta is going to be, what is that? It's going to be 53.13 degrees. So maybe we don't need that, but if we do, we've got that, because here in order to go from O to A, we know in X we go positive 300, and in the Y we go a positive 400. We carry through that. K cross J is a minus I, so that's a minus 400 omega OAI. We get a plus 300 omega OAJ. So that's the velocity analysis we have using the rigid body OA. Now I'm going to look at BC. Well, don't even think about writing down the rigid body kinematics equation between A and C, because A and C aren't rigidly connected. So what I'm going to do is use this observer, the observer that's shown there in the picture. So this observer is going to be attached to BC. And I'm also going to attach XYZ to BC. So with that said, the omega, which is always equal to the angular velocity of the observer, and in this case, since the observer is attached to link BC, it's going to be omega BC K. And BC we know is a positive 6 radians per second. What's the velocity that our observer sees for A? And I'm going to reference that back to, eventually reference that back to C. So it's going to be A slash C relative. So this is the velocity of A as observed by our observer. We don't know what that is. But the observer is going to see A moving along a straight line path, that slot. In actuality, the path of A is a circular path, but our observer thinks it's straight. So he or she is going to report back at some distance or some time derivative L dot align with J. Okay, so with those two pieces of information, I can now use the moving reference frame velocity equation to say that VA is equal to VC plus velocity of A as seen by our observer plus the omega for our observer crossed with the vector which goes from C to A. C is a pin joint. The relative term, that's L dot J. Omega, that is omega BC. K. The vector which goes from C to A, that's going to be simply an LJ. So when I cross this through, I get minus L omega BC in the I. I get an L dot in the J. So this first equation that we got from OA, we'll call that 1. The second equation is our moving reference frame equation using an observer attached to BC. Those two have to be the same. They're describing the velocity of the same point. The I components therefore must balance out. So minus 400 omega OA is balanced out by, on the I components, this one is minus L omega BC. And the J component is 300 omega OA. And that must be balanced out with an L dot like this. So this gives us L dot. That number is going to be in millimeters per second. It's a plus. And all the plus means is that my guess was right. My guess was right in that it was moving up as seen by our observer. So that's good. And then omega OA is going to be equal to L divided by 400. L in this case we said was 400. And omega BC was a positive 6. So that's 6 radians per second. The plus sign that's here means that the original assumption of it being counterclockwise was correct. I think you would agree by looking at the picture that if omega BC is rotating in a counterclockwise sense at this instance, so is omega A. So if we go back to see what we have done, we used a rigid body equation to relate the velocity of A back to the pin joint O to ground. We used a moving reference frame equation to relate the velocity of A back to C. The moving reference frame equation was required here rather than the rigid body equation because A and C are not connected by a rigid body. So we use an observer, this person here, which is riding along with BC, that dictated omega, that's omega BC, K. It dictated what we see here for the velocity of A by our observer. The observer just sees A moving along J. We put those into our moving reference frame velocity equation. We equate the two expressions for VA. We balance out our coefficients I and J, gave us our two equations, one for L dot, the second one, and the first one gives us omega OA.